In this problem, we're finally going to apply all of this trigonometry that we've been learning and reviewing in the course so far. And it's fun to apply trig because you can measure distances. You can think of real-life situations where perhaps you've gone off course and need to get back on course. So here we've got a sailboat or whatever, motorboat, whatever, and it's starting off here and it's got to sail there. What's here? Well, I don't know. Maybe this is the dock over here, and they've got to sail over to some exotic island because they want to go to the beach. But the problem is they sail off course. So originally, from the dock to the island is a distance. We'll make it up, 125 whatever kilometers. Well, if we sail off course, we've got to sail in some other direction that's not on the line. So what if we know that we sailed off course by about 30 degrees? And when we sailed off course, we went a certain distance, let's say, I don't know, 40 kilometers. So we sailed off course at an angle of 30 degrees for 40 kilometers. So then what do we do? Well, we need to figure out how far do we have to go to get back to the island now that we've gone off course. How far off is this distance right here? And I think what you might notice right away is that, wow, what can we do? Because we don't have a right triangle. Right, this angle over here, we don't know what angle it is, and all we know is this angle right here. Well, that's when you want to look for a place to drop a line to make right triangles, right? To use the tool that we have. So I drop this line right here, and now what do I have? Well, I have two right triangles. Excuse me, one right here, and then one over here, right? And we drop the line, we draw these two right angles, and now we're back in a familiar land where we can use SOHCAHTOA. So again, we start off with a triangle. We didn't know what kind of triangle it was, but by dropping this line, it's called dropping the perpendicular, we can create right triangles, and now we can use the trig functions that go back to the very first video in this series. And, well, what do I want to know? Well, I want to know these distances right here. I'm going to use both of them. So let's use the cosine first, because I think it's important to know this right here, right? That would tell me how much is left to get to the island. And this is right here is our adjacent side to the angle, because cosine is the ratio of the adjacent side, this teal side right here, over the hypotenuse. So I'm just going to write down that the cosine of 30 degrees is going to equal this mystery adjacent side. What should we call it? Let's call it A. This little length here is A. So it's going to equal A, the adjacent side, over 40. I'm going to leave kilometers out for now because I don't have so much room. And that means that A is equal to what? Well, it's tempting to figure out what cosine of 30 is right now, but let's just leave it as the cosine of 30 and save that until the end, right? So we have then A is equal to, well, A equals 40 times the cosine of 30 degrees. And because I'm running out of room, I'm going to erase this and just write that again. Okay, so again, what we have here is that A equals 40 times the cosine of 30 degrees, and we'll leave that in there. Now what about this perpendicular right here that we dropped? What's that going to be? Well, we're going to use the sine to figure that out, right? So let me write that in yellow. So that we can use the sine. Sine's opposite over hypotenuse. Well, the opposite of 30 degrees is the unknown. So we have the sine of 30 equals this unknown side here. Let's call this B. Right, we don't know what it is. So that's B over the hypotenuse, which is 40, and using the same technique here, which was, for me, that I picture as multiplying both sides by 40. B over 40 times 40 is just B, and then on the other side of the equation, we keep it balanced. We multiply by 40 again, and we get 40 sine of 30 degrees, and that equals B. So B equals, whoa, what's going on there? B equals 40 times the sine of 30 degrees. So b equals 40 times the sine of 30 degrees. And again, I'm running out of room, so let me just get rid of some of this stuff here. So what's happening right now is that we know these two distances, and we have already forming here in yellow, let me complete that, this is a right triangle. And we can use the Pythagorean theorem to figure out, well, what's this missing hypotenuse over here? And we're going to do that in a moment, as soon as I clear off of this right here. So now that we settle this up, we're almost ready to use the Pythagorean theorem to figure out what the distance is we have to travel to get back to the island, right? To get back from our off course back to where we need to go. And to do that, we just need to think about, well, if this is A right here, what is the distance that's left? And I'm going to just highlight that in orange. What is this right here? Well, that is equal to, you can think of it as 125 minus A, right? Because the whole distance is 125 kilometers. Well, if we take the whole distance and subtract this A chunk right here, we have the orange piece left over, and that's what this is. So how do I figure out the hypotenuse, right? How do I figure out this length right here, which is where the ship has to go from where they got off course back to the island? Well, the Pythagorean theorem is a squared plus b squared is c squared, right? So the square of the two legs of each leg summed up equals the square of the hypotenuse. So let's try that. 125 minus a squared plus b squared. What's b? B is this. It's 40 times the sine of 30 degrees squared. This is all going to equal our hypotenuse squared, so I'll put h here. Okay, what do we do next? Well, we know what a is, so let's plug that in. A is 40 times the cosine of 30. So really what we have here is 125 minus a, or 40 cosine of 30, all of that squared, plus 40 sine of 30 squared, which is just, well, 40 times 40 that's 40 squared. What's that? Well, that's 1,600. And sine of 30 squared, leave the 30 degrees alone, it's just sine squared of 30, and that equals h squared. And since I'm running out of room, let me make a new page and just copy this. We're going to keep working on this equation. And don't be overwhelmed here, we're just going to square this part right here, and I think we'll see some nice things that work out. So let's put this up here. Okay, it's neat enough. And to square this right here, we're just going to expand it. 125 minus 40 cosine of 30 times 125 minus 40 cosine of 30 plus 1600 sine squared of 30. All of that equals the hypotenuse squared. Well, we're going to distribute the 125 to these two parts right here. And 125 squared, 125 times 125, is 15,625. And then we have minus, well, the way you multiply 125 by this, just to multiply it by the 40 right here. We leave the cosine of 30 alone for now because I don't want to deal with that until I have to at the very end. I want to see what can I simplify before I deal with that. And 125 times 40 is 5,000, right? Cosine of 30. And that's going to happen again here because now I'm going to distribute this. So now we're distributing negative 40 cosine of 30. Well, that times 125 is going to be, we're subtracting again, 5,000 cosine of 30. And then lastly, we have plus 1,600 cosine squared of 30. That was just 40 cosine of 30 times itself, negative 40 cosine of 30. And that's positive 1,600 cosine squared of 30. And, wow, I ran out of room. That plus this 1,600 sine squared of 30. And you might see, well, look at this. If I combine these two, what happens? Well, let's rewrite this. 15,625 minus, let's combine these two, 10,000 cosine of 30, right? plus 1600 times the cosine squared of 30 plus the sine squared of 30. And what did I do there? Well, I just kind of skipped this step. If this is 1600 sine squared of 30 and that's 1600 cosine squared of 30 and we're adding them up, you can pull out the common factor, which is 1600, and you get 1600 times the cosine squared of 30 plus the sine squared of 30, right? That's the distributive property. And all of this equals h squared. Well, in a previous video, we talked about how cosine squared of theta plus the sine squared of theta is always 1. So it doesn't matter what the angles are. If we add them up, it's going to be 1. So isn't that nice, right? Those trig identities are very useful. So this is just 1, and 1 times 1600 is just 1600. And I want to add that to 15,625, right? I want to combine like terms. So if I add 15,625 plus 1600, right, what I'm going to get, well, what's that? It's 17,225, yep, minus 10,000 cosine of 30 equals h squared. Okay, now that I've done everything I can, right, I can't just combine these two and have to figure out the cosine of 30 is. Now I'm going to find out what the cosine of 30 is, because if I've forgotten what it is, right, you don't want to deal with it until the end, so you absolutely have to. For example, if I had dealt with cosine of 30 and sine squared of 30 before, then I wouldn't have been able to see that if we just add them up we get 1, right? I was able to simplify those and get rid of them. Anyway, the cosine of 30 is radical 3 over 2. And I can write that as decimal if I wanted to. I'm going to leave it as radical 3 over 2. I kind of like working with that fraction. So that's the radical 3 over 2, right, times 10,000. That's this term. So it's 17,225 minus 10,000 times the square root of 3 over 2, and that's h squared. And we can simplify this. Well, 17,225 minus 10,000. I mean, you would have a calculator for this kind of a problem right here. But we can think of this as, well, 10,000 times over 2, that's going to be just 5,000 times the square root of 3, which is not that much simpler, but it does help, right? So we have 17,225 minus 5,000 times the square root of 3. What is that? Well, that, I'm plugging it in myself into a calculator, is 8,564.745962. That equals h squared. Let's just round to the nearest whole number, because this is our problem and we're designing it. And since there's a 7 here, it's going to be, I'm rounding up to 8,565 equals h squared. Well, I want to know what h is, right? Not the hypotenuse squared. I want to know how long the hypotenuse is. So we take the square root, and h equals the square root of 8,565. So that's going to be what? Well, it's gonna be an irrational number, but it's going to be 92. We'll estimate it to 92.5. And we can round that up to 93 if we want. We're looking at kilometers. That will matter, of course. But what this means is that this distance right here is about 93 kilometers. And in a problem, they would designate what they want you to do in terms of rounding. If they wanted you to round to the nearest whole number, I would wait until the very last step, so even before you found the square root. So what you might have done is leave it as 8,565, whatever it was, 745962. And if you have a calculator in front of you, just take the square root of that. And since I have a calculator in front of me, let's try that. 8,564.745962. What is the square root of that? That's, oh, well, I got 92.545. So actually the same thing. So it's okay if we rounded it there. It didn't change much of the answer. So about 92.5 or 93 kilometers. So just by going 40 kilometers off course and at a 30-degree angle, they have to go 93 kilometers back to get back to the island. And altogether, I mean, if we look at the total trip, we could say, well, that's 93 kilometers plus 40, which is just 133 kilometers. So they only had to go 8 more kilometers than if they had gone in a straight line, which is surprising to me because I feel like if you had gone off by that far, wouldn't you have to go a lot further to get back on course? The answer is no. It's only 8 kilometers more, right? 90 plus 40 is 130, and then 3 more kilometers, that's 133 kilometers to go this way. And that's only 8 more kilometers than if they had gone straight. So anyway, that's a way of thinking about trigonometry and how it can apply to course plotting on the ocean or really anywhere.